I'm going to take the square root of both sides, okay? So I go here, I take the square root here, and that means this becomes omega c times square root of mu epsilon. Do you all agree with me here? Right? Keep watching. Now what is omega c? Omega c is 2 pi fc, isn't it? So I can say this is really going to be 2 pi fc. Follow me? That's what I want, the cutoff frequency. That's what he asked about. With me on this class? Now, after that, I divide everything by pi. So if you divide by pi, bring it inside the square root, it's pi squared, right? Do you all see all the pi's go away, class? Can you see that? Can you see it in the back there, guys? So I'm going to just erase them. I know some of you might not like doing every single equation, but this is just slight modifications. Now after that, I'm going to divide by 2 and the square root of mu epsilon. And let me do it this way. And that is FC. Now, can somebody just tell me what is 1 over the square root of mu epsilon?
C of
In free space, it would be the speed of light, right? But it's really the velocity of propagation in an unbounded media, if it's not in a waveguide. Follow me if it's just mu and epsilon. So just remember, you can put, especially if it's filled with air, you can just put C here. All right? If it's air-filled, you can put FC. This is air. It's air-filled. FC is equal to C over 2 times square root of M over A squared plus N over B squared. That'll work for an air-filled guy, and I think this one's air-filled. All right, now we talk about where do you begin with the integers. M and N are integers, right? And A is greater than B. The lowest order mode that will propagate will be the TE10. I'm going to tell you that, and I'll prove that, but you're going to get a TE10 is the lowest order mode. That is when M is 1. That's the variation across X. And there is no variation in the Y direction. Now there is no 10 mode in the TM for TM, and here's why. If either one, N or M or 0, there is no field in the Z direction. Do you all see that? But for the TE mode, here, you will have, if it's 1, 0, there's still a mode. It still will be non-zero. Do you follow me that? So that's important. The lowest order mode that you can get is TE10. And the value of that would be, the cutoff frequency for that would be equal to, if it's air-filled, C over 2 times the square root of M over A squared, but here M becomes 1. I want to do this completely here. Do you all see what I'm doing here? Just look at the equation. Put M equal 1, N equals 0. This is the lowest order or the lowest frequency that will propagate. Above that will propagate. With me? Y'all see? I'll put the dimensions in a second. Now, for that problem, I'm going to give you a heads up. I'd never ask something like that on a test. I'd ask for the lowest order mode and the next lowest order above that, the next frequency up, but I'm never going to ask for none of them. That's redundancy. Do it on MATLAB. I'm not going to ask that in class. But you have to know the lowest order mode, and you have to know it's TE, and then the next lowest order mode that I'm going to get to in a second, all right? So here, what do you notice that is? That's the lowest order. The cutoff frequency for the 10 mode is just C over 2A, C over 2A. That's the lowest order mode. A, C is in meters per second, A would be in meters. With me? After that, the next one would be what? Well, now listen to me. If A, right here, is twice B, and it usually is greater than 2 times B for a reason, then the next lowest order mode would be 2O. Do you follow me? Then after that, the next order mode after that would be O1, where this is 1 and this is 0. But this is just the order, depends on the dimensions. In almost every case, for normal waveguides, They make it so the first lowest order mode is a 1-0, and then it's 2-0, and then 0-1. All right, where N would be 1 and M would be 0. Do you follow me? And they're all TE. Correct, class? Just understand, I'm trying to give you a heads up, and we'll spend more time on this. So, he asked me for 9, right?
8, but
8.
if you do like 2.
The only thing you do is take this M, N, and just put it equal to C over 2, square root, and then you put the dimensions in here. It's M, what's A?
A was, sorry, flipped over somewhere else. A was 0.9 inches, and B was 0.3.
You gotta change it to meters.
Right.
All right, that's a common mistake. You gotta put everything in meters, whatever the conversions is. 0.9 inches times whatever that gives me meters, get that. And what is B?
B is 0.3 inches.
All right, this is reasonable, 0.3 inches. Can you see how A is at least twice B? It's actually 3 times B. That's normal. They make sure it goes from 1-0 to 2-0, and the reason is this, and this is important. We didn't get there yet, but the velocity that energy propagates down there has to do with the mode it's in. What you normally do is drive a waveguide just at a frequency beyond the 1-0 cutoff frequency, but not to the 2-0, all right? So from between 1-0 and 2-0, you drive in there. If you drive above 2-0, then there's 2 possible modes. There's 2 possible velocities for energy or power propagation. And what that does is garble everything. If you have energy or power going down, regardless of how much is split, and some of it's moving at C and some of it's moving at, say, 0.5 C, then when you go and it assembles itself at the end, you get garbling if it's communication signal. You understand that, class? So when you propagate, you only want one mode. The only time there are exceptions is if all of a sudden I'm going to send energy at 2 different modes, but I'm going to extract that energy in 2 different ports. I'm going to get one of those ports pulling out, say, energy in the 1-0 mode, 1-0 frequency, and then the 2-0 frequency I'll have a filter on, and I'll pull out energy there. And these are extreme cases. Almost, I've never had to do that, but that's one of the reasons possibly for doing that. There's some other oddities, but really for the most part, at least your first crack at this stuff in the real world, you're just going to be propagating energy in one mode. Almost guaranteed. And it's just above you're going to go about probably 30%, 40% above the cutoff frequency. Yep.
Are the frequencies for cutoffs like inclusive?
What's that?
Is the cutoff frequency, is that the frequency where it starts propagating?
Yep, anything above there. You normally don't go right at the cutoff, because at the cutoff, energy is bouncing just back and forth on the guide, like a parallel plate capacitor, just ricocheting. Then you go a little bit above it, then it's banging like this, going down. And I'll get to that. This is M over A squared plus N over B squared. So when you do this, and you can do this in MATLAB in a heartbeat, you write this equation down, you put in the value of A in terms of inches, right, and B in inches, and then you just say, for M equals 1 to 3, for N equals 1 to 3, find this, and then print this. And you'll see, did anybody do this one in here? If you do it, what you're going to see, it's very predictable. 1-0, 2-0, and then 3-0 will be 0-1. There'll be what's called a double mode. Because when this becomes 3, right? When you have 3 in the A value, and when you have 3-0, it'll be exact same frequency as 0-1, because B is 3 times, or B is 1/3 the value of A. You follow me in this class? And that's called a double mode, where 2 different ways energy sets up, or the electric field pattern maps in 2 different ways and superimposes and propagates. You don't have to worry about that. Right. Those kind of modes, you just use one frequency there. Anyway, if you do that, you'll get it. And honestly, this is kind of a simple thing. But the lowest order mode you have to know, and that is right there. And then the next lowest order mode will be when this is 2-0, right? Do you all see that? That's usually all you care about. I'll do the separation of variables in a second, but I want to hit some high points there. Now remember, what was the real thing you wanted to know when you had transmission lines? What was the key thing? You wanted the characteristic impedance, right? You wanted to know what was the load, and you wanted to know what the source resistance was, and then You could easily calculate the standing wave ratio and anything like that before you did matching. Do you all agree with this, class? Most of the time with waveguides, you don't do impedance matching. At least I'll level with you, I never have. The reason is they make sure the load is impedance matched before they put it on. Now, what normally happens is, I say that, and Riggs is probably gonna find something where they tell me I was wrong because they did this at Harris, but I'll deal with him later. What really happens most of the time is that you have an antenna and they make sure the driving point in that impedance of that antenna is the same as the waveguide. Follow me? Or if you have an amplifier that you're plugging in, it will have the same output impedance as the waveguide, so it's impedance matched. I'll show you how they drive these things in a bit. But just realize it's just like, now it's just like transmission line, baby, all right? So what about the impedance? Can you all understand what I've done here? The rehashing? Did you have another question you want to ask me before I move on?
I'm all right, thank you.
Does anybody else have a question about the homeworks? They were just plug and chug, right? How many did that homework? I'm getting a look from you like, I don't know what you're talking about. You did it, thank you. I mean, wasn't it just plug and chug, really? There's nothing tricky about that homework.
Well, one said do 7.3, the other one was 7 point, and there's not a number after the point.
Are you kidding me? Shoot me an email whenever something stupid happens like that, because I put that up there. Sometimes I don't know some of these things happen. I should have re-looked. Today I'm going to tell you what you really need to know about waveguides when you're out in the field or you're doing waveguide engineering. And I'm not talking about critical design or something like that. I'm talking about just applying waveguides. The way they're meant to be applied, like transmission. Has anybody ever done, I got a question, because I always wonder about students these days. When I was where you were at, cable just became popular. Literally, it was 84, 85. And I remember stringing cable, getting a splitter, putting it to two different sets or whatever. We didn't have internet at that time, we just had TVs. Going ahead and learning about how to do that kind of stuff on my own. And if ever you try to split a signal 4 or 5 different ways, you realize the power starts going down. And the longer your cables, the bigger the problems you get, right? So as electrical engineers, you learn all about trying to assess how much you lose in power in terms of dB per meter. And if it's impedance mismatch, like cable Cox, well, Cox and Charter, their cable, or whatever it is now, Spectrum, their cable is 75 ohm cable. Most cable we use in our laboratories for microwave work is 50 ohm. So what some bright student will do is find a way to have 50 go to 75. It's impedance mismatch and he's not getting any power out. I have not done this personally, but I know enough about students that this is a typical kind of ploy. If it doesn't fit, get a bigger hammer, and punch it in there, and I'll make it fit and then nothing works. It's normal. I've seen some really bizarre things in my life. Thank God most of the electrical engineering students, by the time they're where you're at, they're not gonna do things that stupid. But other students have a genius for destroying things, doing that kind of stuff. So now we're going to get on to the waveguide aspects of this. Please understand the mode you operate in is usually TE10, all right? Here's the difference. Yes, did you have a question? Okay. Between TE and TM, there's a different impedance. So when I talk about the characteristic impedance of the guide for TE, all right, for TE modes, it's equal to just the characteristic impedance, mu over epsilon of whatever's filling the guide. That's like eta naught, understand? The mu and epsilon of the material in the guide, the dielectric, and usually if this is ever not mu relative equal 1, mu naught equal to 4 pi times 10 to the minus 7, there's something very odd going on. They might have a material that actually has a filtering property, but I've never ever seen where mu isn't just mu, just plain old mu naught. Now epsilon will change values. Then you divide this by the square root of 1 minus FC over F squared. Now that FC has to do with the mode it's operating in. You follow me? So if it's a 1 ohm mode, it's the cutoff frequency for 1 ohm. If it's a 2.0, it's the cutoff frequency for 2.0. And because this crops up so often, what I do is call this K. I just say K is equal to the square root of 1 minus FC over F squared. Remember, F is the operational frequency. And I want you to take a look at this for a second. What happens to this value, the impedance, as the frequency goes to infinity? Well, FC has a certain finite value, right? But as the frequency goes to infinity, this goes to 1. As frequency goes to infinity, the characteristic impedance just goes to the characteristic impedance of free space. Because then it doesn't look like a waveguide, it looks like there's a plane wave propagating. You follow me on that, class? All right, that's for TE. For TM, it's equal to the square root of mu over epsilon, and that's just times K, not divided by K. Here, wouldn't this be equal to the square root of mu over epsilon divided by K? Is my K up there? Do y'all see that, class? If you look at his book, he has ZTE and ZTM. If you have your books, can you tell me the page it's on? If you got it there?
391.
391. And he should break it out into two different TE and TM modes, does it? He should. It's characteristic impedance TE, TM. Yeah. Yeah, there's TM is 755, and where's TE? I like putting them right beside each other. Right here. TE is 779 on page 398. Put them next to each other, and this is the key thing, just remember that. Now, TE modes, as you get close to cutoff, that impedance goes to infinity. Do you see that? So this is important. When you've got a TE mode, which most of these are, the 1.0 mode, if you're, just think about this, what happens if you're at a cutoff, say that your frequency 50% greater, say twice cutoff. Well, then you would have 1 minus 1/2, right, squared, or 1/4, you would have the square root of 3/4, wouldn't you? So it would be really the characteristic impedance of the media divided by the square root of 3/4. That's about the characteristic impedance of the media, so it's not a big problem. But if you try operating like at the really cutoff frequency, maybe 1% greater than that, then this impedance gets very large, all right? So you want to operate away from the cutoff frequency, but not into the next cutoff frequencies range, because then you get two modes. So you want to make sure you're between the first cutoff and the second cutoff, probably 60% the first cutoff will do you, and that'll be fine. Follow me? This is just some advice. Now, me personally, I know there's applications. Most of the time, this is what you use, 1.0, almost 95% of the time, maybe more. You'll use this once in a while. Now, here's where you use it. Not with rectangular waveguides, but with circular waveguides. He doesn't do circular in his book. In circular waveguides, they do both TE and TM propagation, and the impedances are different. Follow me? We don't have that in the book. I may cover it if I have time, just because of the applications. Most of the waveguide engineering you see is going to be using rectangular, but when you're talking about things where you want right circular polarization or left circular polarization waves, and this comes later, well, actually we talked about that, then you want antennas that can support those, and these are, I'll get to this, are cross poles, and then you use circular waveguides, because you want to be able to send out right circularly polarized and receive left circularly polarized and have filters to do them off, and that happens when you have cylindrical guides. And that's not in his book. If I have time, I'll cover it, but I'll cover it in a way that you'll appreciate and not get blown away by the theory. I'll try to put it as applications oriented as I can. So when I talk about a waveguide, I am going to do that separation of variables, but before I do, this is more interesting, I think, to you. It's an application. So what kind of a problem will you get? Not in Whitmore's book, by the way. I'm going to give you these. Here's a typical problem. I have a source voltage. Write this down. At a frequency, some frequency of operation. I'm going to have a source resistance, and then I'm going to have a waveguide. Now, here's where the guide's going to be. I'm just going to show you it like this. I'm not even going to try to draw everything. The way these things actually are fed is they put a little feed antenna here. It's a short little antenna into the guide. They cut a hole, put it in there, And this antenna is set up so it will energize the mode of propagation, like the 1-0 mode. And I'll get to the actual field patterns later. Follow me on this, class? The 1-0 mode has a distinctive field pattern in the antenna. It has no variation in Y and no variation in X. And what it actually looks like, we'll get to the field quantities themselves, but I'll just tell you this. If you took a cross-section of the guide and took a snapshot, froze time, and looked at the electric field, here's what would happen. You would have, and I'm just going to try this, in every point vertical, you would have these things that are the field, electric fields. And if this is the x-axis and this is the y-axis, you would have something like this. Now, this is hard for me to draw correctly. We'll go right to 0. But you see how that field pattern, this would be the E field I'm trying to show you in terms of picture. And that same field pattern would be at the very bottom here, right in the middle where y is equal to, say, b over 2, and right at the top. Follow me on this? It will not vary with y, but it varies only with x. Do you follow me? Can you all see what I'm talking about here? That's a TE10 mode. That energy propagates. Something to note here. You'll notice this is exactly a half wavelength. Right? You all see that right there? That's a half wavelength. And that's the way it will always be. Now, what happens at cutoff, just so you can get an appreciation of this, what you try to do is stick in a wave that doesn't fit. You would like that one to go in as a 1-0, but it doesn't fit. You see how these sides short that out? So all that energy is shorted out. It's called an evanescent mode, and I'll speak more on that in a bit. Can everybody, I'm trying to give you an appreciation for this without doing the math, the hardcore math. Do you all see what I'm talking about? That's why waveguides only have higher frequencies. Has anybody done anything with any kind of sound engineering or have you ever noticed the narrower the pipe, the lower the frequency, the higher the frequency it takes to propagate energy? Does anybody notice this? You did, you were bound. Anybody does anything in physics with sonics or anything like that, you'll find the narrower the pipe, long pipe, it takes a higher and higher frequency to propagate because it really has to do with the half wavelength across that pipe's diameter. The minute that frequency, and this is sound of course, is not that or higher, it won't propagate. And it'll just die. And that happens with everything. Now, give you an appreciation for that. Back to my waveguide engineering problem. So let's assume right now we're TE10, 1-0 mode. And I'd give you dimensions of the guide, A and B. Follow me? So I'd have A and B. And I'm going to say it's only going to propagate in the 1-0 mode. So you know this waveguide of mine is going to be attached to a horn. And I'm going to put that horn attachment at z equals 0 here. And I'm going to make this distance back here be z equals minus L. And you can kind of know where I'm going. That means the guide itself has a length of L. Follow me, class? It's just like transmission line problems. Remember, you always put the load at 0. You drive it at minus L, z equals minus L. Follow me? You remember this from transmission line theory? Give me a show of hands. So I know I'm talking to people that understand. Y'all remember this? All right. Now, that's the load. What does this really look like? It looks like this. Here's your VS, here's RS. And then you can just say, this is just like a transmission line. And here is going to be some ZL here. Now, this has a characteristic impedance for the waveguide. But that characteristic impedance right there, first you have to say that that characteristic impedance would be equal to really the square root of mu over epsilon of the guide over square root of 1 minus FC over F squared. So now you got to calculate FC based on this equation, right? Or I should say that's K. Your FC, you actually get FC for the 1-0 mode is equal to C over 2A, right? Remember I showed you that what it reduced to when n is 1 and n is 0, class? That's what you get. You calculate that. You come here and you find the characteristic impedance. Follow me? Now once you have the characteristic impedance, the impedance looking into this guide, just call this, say it's Zn, is identical to the equation that you used before for the input characteristic impedance. Some of you remember it, There's one caveat that's about to come. So this is gonna be equal to that characteristic impedance. It's ZC, and I'll put 1O mode, times, and then it's gonna be ZL here, plus JZC 1O times the tangent, but now this is gonna be tangent of beta in the guide times L over, I'll get out of your way, don't worry, ZC 1O plus JZL times tangent of beta in the guide times L. Let me erase this right here.
Could you just run it a little bit higher to the right?
I'll tell you what, I will. Let me do the whole thing up here. How about right here? Zn, this is gonna be input characteristic impedance right here, is gonna be equal to Z naught, or ZC 1O times, and then this is gonna be ZL, whatever ZL is, plus J Z naught 1 over ZC 1O times tangent of beta, and this is beta in the guide. I'll get that. All right. Beta in the guide times L over ZC10 plus JZL tangent beta in the guide times L. Now you remember before, this was just Z naught in your wave guide, or I'm sorry, in your transmission line equation, right? So this is the difference. There's one other difference too, beta in the guide, right? Hear me on this one. What is beta in the guide? Well, beta in the guide times lambda in the guide is equal to 2 pi, or I should say, I'll just write this down. So this is equal to omega times square root of mu epsilon, that's beta unguided, times the square root of 1 minus the quantity Fc over F squared. Let me spend a little bit of time talking about this. Remember before when I had that equation for beta Z back here? Beta Z is beta in the guide. You follow me? Because it's the beta in the direction of propagation in the guide. Everybody got that? Now remember it cut off at 0. Do y'all remember that, class? All right, take a look at this equation here. I said beta in the guide was beta unguided times this. Now if you're a cutoff, F is equal to Fc, right? So 1 minus 1 is 0. The beta in the guide goes to 0. Do you all see that? As frequency gets high, it doesn't matter the mode, by the way. As frequency gets higher and higher, all of a sudden, beta goes to beta unguided, like a plane wave. Can you all see this, class? So that's what this beta in the guide is right there. It's unguided times k, if you will. Do you all see this, class? How many understand what I'm talking about here? Because this equation requires beta in order to work. L would be stated explicitly, but beta wouldn't. Follow me on this? It's important. Now, if that's beta in the guide, well, what is wavelength in the guide? Well, lambda in the guide here, all right, would be equal to 2 pi over beta in the guide. Are you with me? Everybody follow me on that? Just like, you know, what is wavelength? Well, it's 2 pi over beta. That's the most fundamental definition, right? All right, now, getting back to this problem that I had. So, I'm going to erase this and I'm going to do it for you. I'll get to my little, the TM mode business in a second. If you looked in the book, you saw that he had all those field equations for EX, EY, EZ for the TM mode, and for the TE mode, he had EX, EY, and then all the H values. So how do we do this problem? Here's my goal. on this one. I want the voltage at the load, and I'm just gonna show this as a length L here. And what I want is I want this voltage. I want V on the load. Then I want power in the load. Now here, I want the voltage in the load, and I want the power absorbed by the load. This is important that we see this. All right, so for starters, all the waveguide problems I'm going to give you are going to be lossless. You can write that down. And you will be given some mu and some epsilon. Almost always it's air filled. Occasionally, if I give you one with a pressurized gas like argon, I'll give you the value of epsilon relative. All right, that's the only thing that would change. So almost always, when you talk about the square root for air, I know that the square root of mu over epsilon for the guide is really just eta, right here, eta naught. Do you follow me? 120 ohms. 120 pi ohms, pardon, right? 377 ohms. Now, keep watching. So how do I do this problem? I start by saying, just like the other ones, I want to find the voltage just inside there. So now what I need first, I have to take care of, and I have to, this is really the way you do this. You find Z input, which is equal to ZC10 times ZL plus ZC10 times, J times that, times the tangent of beta in the guide times L over ZC10 plus J ZL tangent times beta in the guide times L. I tell people when you're doing this, the smartest thing to do is calculate the tangent of beta in the guide times L and put it in your memory, and then just recall it. Because don't keep punching all those numbers. Just store that in a memory unit. That way you can recall it. And you basically have ZL and ZC10. Now, ZC10, again, ZC10, if it's air filled, assume air here, is just going to be equal to what? For the TE10 mode, it's going to be equal to 120 pi over the square root of 1 minus F over F, FC over F squared. So you get that, then you put it in here, and you put in for ZL. I'm not putting in actual values for ZL, I'm letting you do, this is the general way you do it. Follow me? And this is just like the transmission line problems. At this point, what we do, now we say that the voltage, I know it's really an E field, but it's a measurable voltage too. The voltage just inside here, I'll call it V prime. Now we say V prime will be equal to the source voltage times Zn over Zn plus Rs. Can y'all appreciate that? Remember doing this in the transmission line problems? Now we get the voltage just inside the transmission line, right? With a waveguide, you get a voltage from the very top of the waveguide, the middle of it, to the very bottom, middle of the guide. And that is going to be a voltage. All right? And it's measurable too. So that's this voltage. Now that's the voltage just inside, right? Y'all remember doing this when you did the wave? How many do when you did transmission lines? Every one of you should have done this several times. If you had me, you did. Now what is that equal to? You remember how it's equal to a positive traveling wave, V0 plus, right? Times e to the minus j, and here it's going to be beta in the guide times z, plus some v0 minus e to the plus j beta in the guide times z. Remember that? And how do I find out what the ratio of v0 minus to v0 plus is? What did we call that? Anybody?
Standing note.
Reflection coefficient, right? The ratio of the magnitude of the reflected wave to the incident wave is the reflection coefficient. Y'all remember that? Right? How many do? Come on, you just mad at me about something. I know you know this, right? All right, well, what is the reflection coefficient in general? It's always the impedance you're going into minus the impedance you came from over the sum of the two, correct? For this one, well, the impedance I'm going into is ZL, right? Now the characteristic impedance I came from is minus ZC10, right? That is the characteristic impedance of the guide at that frequency. Does that make sense to everybody? Over Z of the load plus ZC10. That's the reflection coefficient. All right? Once you have the reflection coefficient, you can come back here and rewrite this equation. I'm going to slow down for a second because I'm probably going to get some hate mail if I don't. So I can rewrite this equation and say that means this is really equal to V0 plus times e to the minus j beta z times z plus the reflection coefficient times e to the plus j beta z times z. Do you all remember doing that? Putting in a reflection coefficient, taking out the V0 minus, right? Now, we need to calculate V0 plus in order to solve this problem. And do you remember, anybody remember how to do it? Remember, we've got this, right? We've got, remember?
But Z is 0.
You put Z equal minus L, right? Because what we want to do is, right here, we know what the voltage is, just on the inside, don't we? Correct, class? So we equate that to V0 plus times e to the minus j beta z times minus L, not plus L. Here's what we actually do. We take this equation right here. Remember, I've got that. And now I'll just show you what I do. This is equal to this, right? I'm going to get rid of this interim step right here. And I'll do this. Now if I put Z equal to minus L, that becomes plus, and that becomes a minus, right? Y'all remember doing this? And now I can calculate V0 plus, and I'm going to do it, just write it here, would be equal to this, which is, I'll just leave it as V prime, and that's over e to the j beta z times L plus the reflection coefficient times e to the minus j beta z times L. This is not in his book. All right, he does not have this, but this is important. To do waveguide stuff, you've got to know this. If you've got an impedance mismatch, you have to be able to do this, okay? And then you can get rid of the impedance mismatch with actually a stub. But y'all agree with me there? Plus? All right, now, that's V0 plus. My question is this. I wanted the voltage right here. That point is at Z equals 0, isn't it, class? I mean, remember how we always have the z-axis there, and we always put the load at 0, right? For a lot of reasons. Mathematically, it makes it simplest, probably. So this is V0 plus. Remember, that's beta in beta z, so you need to get, that's beta in the guide. All right? That is not just beta, omega squared and mu epsilon. So now I get this V0, and the general equation for voltage is Vz is equal to V0 plus times e to the minus j beta z times z plus the reflection coefficient times e to the, and this is going to be plus j beta z, or beta in the guide, times z. So I have gamma, I've got V0 plus, and now I want the voltage at the load. Or where is the voltage at the load? At what position in Z? 0, so you just do this. Put a 0 there, and that becomes via the load. When that goes to 0, y'all notice what you get? This is just 1 plus the reflection coefficient times V0 plus is voltage at the load. Do y'all see that, class? How many do? Now, what is the current at the load? If you wanted the current at the load here, what would it be? And it's as obvious as you think. Well, current at a load would just be equal to voltage at the load divided by ZL. You all agree with that? I mean, that's it. Now, what is power at the load? It would be, I've heard it right, the power absorbed by the load, this is average power, would be equal to simply 1/2 the real part of V at the load times I conjugated at the load. Can you all understand that, class? There's other, what you're going to see is this is basically going to be a v squared over the magnitude of ZL times the cosine of the angle associated with ZL. But I'm gonna leave it like that for now. Okay? If you want, I'll put the other one up. Some of you probably do. Another equation for this, and I'm gonna write it up here so y'all can see it, is this. You could say power at the load was equal to 1/2, all right? 1/2 times magnitude of VL squared over magnitude of ZL times cosine of the angle associated with ZL. Like if ZL was 50 plus J 50 ohms, all right? That would be equal to a magnitude of 50 times square root of 2 and an angle of 45 degrees. Do you all follow me? So that angle would be cosine of 45 degrees. All right? I hope this is helping. Now, getting back to the actual doing the separation of variables and then finding the field quantities for both TE and TM. We did all of TE. Remember when we got the E field for TE? Then to get the other field quantities, I'm not going to have enough time today, you do the curl operations, you can get all the other field quantities. Remember, there is no HZ, right? Only an EZ for that mode. For the other one, when it's TM, all right, or sorry, for the TE mode, there is no E field in the Z direction. It's all magnetic. So, now it's more fun. Oh, one other thing I gotta tell you, and this is physics related, it's phase velocity versus group velocity in the guide. I wanna do that right now before I take off on this proof. Does anybody know if it's supposed to rain today?
I think it's tomorrow and Friday.
Well, I hope it rains soon.
Today's just partly cloudy.
This guy's bigger than home as well.
This has been a hot September. My yard is
It's a cool 89 degrees outside.
Now, next thing I'm going to tell you is how to get phase velocity and group velocity. In general, first, I've got to put beta in the guide here is beta Z, right? And that's equal to beta unguided, right, times square root of 1 minus FC over F squared. I keep writing that down over and over again, and I encourage you to do that too because it'll stay with you. The more times you say or write something down, the more likely it is to stay here. And you remember it. Now what is beta unguided, by the way? That's what? Omega times square root of mu epsilon for lossless cases, right? Where mu and epsilon are the constitutive parameters, or constituted parameters of your rigs in the actual waveguide. Now, I have that. And when I look at phase velocity, first, wavelength is 2 pi over that, correct, class? So, I'm sorry, 2 pi over beta unguided, all right? Now, what happens to beta unguided at cutoff frequency? What does it become? Just look up here. At cutoff, what does it become? Can you all read my writing? It's 1 minus FC over F squared. Well, if FC is F, that's 1, right? 1 squared is 1. 1 minus 1 is?
0.
0 times beta is 0, right? Now, if it becomes 0, what does the wavelength become? Infinite, right? That means basically if you've got an infinite wavelength, it means there's no variation. And energy at cutoff is just bouncing top plate, bottom plate, top plate. It's like a resonant cavity at that point. With me? Now, that's you're not gonna like that, but sorry. Apologize for this shutting down the phone. That's wavelength of the guide. Goes to infinity at cutoff. What is phase velocity, you think? Well, what's phase velocity in general? Isn't it omega over beta generally, right? But now, what beta are we going to use? Beta in the guide, right? So keep watching. This is going to be equal to omega over beta in the guide. And that means it's equal to omega over, well, what's beta in the guide? It's beta unguided, or omega times square root of mu epsilon times the square root 1 over 1 minus the quantity FC over F squared. Can you all read this okay? What's the one thing you notice here? Just let me finish this. Give me another 30 seconds to a minute, I'll be done. What do you notice about this equation? Well, how many see that that the omegas cancel? That's the starter. Do you all agree with that? It does. Second thing is, what is 1 over square root of mu epsilon?
Velocity.
It's really the velocity in an unbound region, right? So it'd be velocity, phase velocity in unbound region, right? Now, what happens to that velocity as you approach cutoff? It's tending to infinity, right? Now, phase velocity is misleading. Let me just get this through. What am I talking about when I say phase velocity? I want you to appreciate this. If this is, say, a shoreline, and I have waves, ocean waves, moving like this, right? They're moving at a certain velocity this way, right? Now go to a crest of a wave, assume that's the high point, and look at how fast this point where it intercepts shore is moving. That's phase velocity. Can you see as this wave starts coming in almost normal that the phase velocity there is approaching infinity? You all see that? Because phase velocity means literally how fast a point on the wave that has the same phase is moving down the guide. It has nothing to do with energy. Well, it does. Do you all follow me on that? How many see that? Now, how fast is real? If you think about it, when waves in a guide, if this is a wave guide, when they're just bouncing up and down, right? Nothing's propagating, right? But if they're bouncing like this, then they have a component of velocity in that direction, right? Well, that's the velocity of energy. And the velocity of energy, and I'll spend more time on this, or the velocity that's called a group velocity, this is the velocity of energy, is simply the velocity in an unbound media, or really it's going to be 1 over the square root of mu epsilon here, squared, divided by the phase velocity. So you would put this equation in there, and you're going to find out that the velocity of energy propagates at 0 meters per second at cutoff, but then it approaches the velocity in unbound media as frequency goes up. Last thing, both phase velocity and group velocity become the same thing for high frequency as you get much, much greater than the cutoff frequency. I'll leave you go there. I wanted to get through there, I didn't get through my separation of variables. Now somebody should ask me, well, what about a quiz? I'll be happy to give you a quiz Friday. As a matter of fact, what we'll do is cover things related to waveguides based on, say, the cutoff frequency and that little problem I did here, and I'll give you some problems related to it, okay? Friday, quiz.
And the quiz could be like on the, what we just did?
Yep.
Not-
I'll give you homework on it. Don't worry, you're not going to be blindsided.